Okay. So I think today Abu is joining us online, right? Because I think usually you are attending classes face to face. This is C, and again this is a shaft. So our today's topic is stress concentration. Now, just a quick remark. There are students who are wondering what is stress concentration. So I think we can wait for 3 minutes. Then I will start explaining.
Hocam, did you check strength homework time? I sent an email yesterday.
To me?
Yes.
About what?
Created homework for I think its time is wrong. It's
time is wrong. Oh, sorry. Yes. You sent me an email. Now I remember. I will change it.
Okay.
I will change. If we have a 5-minute break, I will go to O2 class and I will change it. In fact, I will postpone the deadline to 24 hours. We had another student who said, can you postpone the deadline because we have exams? So in fact, the deadline of today's homework that is supposed to be 11:55 p.m. tonight, I will put it to tomorrow 11:55 p.m. Okay, yeah, okay. I thought in strength of materials, we don't have time, not like dynamics, but then I realized you were talking about the O2 class time. Okay, so, okay. So there are students who are saying, what is happening? Well, my point is that you have this sudden change in the dia, and exactly like normal stresses. So we will explain at 10:40, by the way, we still have time. Okay, so we have good morning. So we did talk about 10:39. Salam, good to see you. So we have okay, and again a non-linear. Oh, come on. This one is again tangent. There are students who are thinking. Okay, welcome to another session. Just to clarify something, if you're used to do something like in normal stresses, in the normal stresses, we used to talk about stress concentration, right? So if you remember, we used to have, let's say, a flat plate, and there was a sudden decrease in the dimension of this flat plate. We used to talk about the fact that you have this sudden change in the dimension. So there would be stress concentration, and we talked about that K, right? So in this torsion topic, we will actually go for the same strategy. Now I have in a shaft that is rotating, sudden change in the dia. And now again, I will talk about a stress concentration. Now for students who are like, come on, what does that even mean? Well, my point is that you have this nice and beautiful circular shaft. And if you remember, for torsion, I used to talk about that I will have the shear stress is equal to TR over IP, behaving like somewhat like this. Okay, I will give my best shot in this drawing. I used to tell you, nice and beautiful, boom, right? Too many drawings, by the way. And then we used to say there is a linear variation, right? Now, I will take the discussion one step further. Now I will say that although this is what we talked about, that in a circular shaft, I hope I am doing justice with the drawings. you know, right? Okay, so I'm definitely not going to do it. I think you understand how it is behaving linearly. Actually, your stress concentration, because of the fact that you have a sudden change in the dia, you will have a rather non-linear behavior of these lines. And let me make another line like this. This is going to be a little hard. Please bear with me. Come on. Yes. And then another line here. So it will be no, it will be non-linear. Let's call this variation non-linear without knowing the exact shape. Oh, come on. So the black line is something life was beautiful because of the fact that now you have stress concentration. And for students who are saying, what does that even mean? I will very quickly make these arrows. The stress lines are trying to squeeze themselves in through this little fellow. Oh, come on, right? Okay, so again, my strategy remains the same. I will say that this shaft has a dia of 7.5 inches. It has a fillet of 9 by 16 inches. It has a dia of 3.75 inches. Okay, and what was the formula, if anyone remembers, for the K?
Maximum stress by
Yeah, allowable divided by, very good. So here I will say shear stress allowable divided by shear stress average. And you know what? I think I need to give you a torque as well. So I will say that this shaft, which is again one continuous object, question says rotates. By the way, how many of you have a hard copy of the textbook? Did anyone have it like from library? Just to have an idea. No? Everyone uses soft copy like me? Okay, rotates at 900 RPM. The allowable shear stress is 8 KSI. You can tell me the meaning of KSI? Kilo pound per square inch or kilo pound per inch square. Very good. Okay, and then question says you have to give me the maximum power. Now, the same story. Because of the fact that there is a sudden change in the dia of the shaft, you will have now maximum lines, the ones in the red. You see, big lines. They might exceed the allowable value, and you don't want that. So now what I will do is, it's not linear anymore. I will, I will solve this question now. So unfortunately, I cannot because I need a chart. So what I will do is I will quickly open the textbook, which I haven't. So please bear with me. 5, 4, 3, 2, 1. And one of you needs to remind me to resume that, or probably we can just resume. That's
Don't you need the diameter of the middle part for finding the stress concentration factor?
Yeah, that is, sorry, this is dia, not the length. Oh, where is the pen? Yeah. I think I should have clarified. This is dia, not the length. I have to clarify. This is dia. So this is dia. This is the dia and the fillet. Yes. Okay, bear with me. Screen. Where is the book now? Let's find the book. Okay, that's why I want to pause the recording. Please remind me. Torsion is included in your midterm exam one, just to be clear. So please remember these topics are also coming. Now I will scroll and I will go to the chapter 3. Come on. Okay. Then I will try to go for stress concentration in my textbook for torque. Statically indeterminate shafts, we went through it. last week. We talked about it last week. Then I will open stress concentration. Stress concentration in circular shafts. I hope our in-class students can also see. Dogukan and Ebu, it's clear, right? You can see, right? Okay. Hang on. Boom. Got it. So now this is a nice and beautiful chart. So what does it say? It says that your x-axis has small r over d. What is the small r?
The radius of the fillet.
Radius of the fillet. And I think when the radius of the fillet is very, very, very small, then the corner will be very sharp. When the corner is very sharp, it is more prone to it's more prone to tearing apart, more prone to failure. So that makes sense that when my R keeps on going smaller and smaller, the K value gets larger and larger. So things are making sense. Now what I need to do is to crack this problem, I will find small r over d, where d is the small dia, number one. Number two, I will try to find capital D over small d, where capital D is the dia of the big shaft. I apologize. The bigger part of the shaft, of the same shaft, and small d is the small dia. So r over, bear with me now, just, so I think you can do the problem now. Quickly do it. Small r over d equal to, you do it yourself. Capital D over small d, you do it. Things are making sense, right? Acha, 0. Very nice. 0.0.
0.50, not 0.0.
Oh, sorry, 0.15. Yeah, okay. 0.15. And capital D over small d is 2. Good. Done. Now what I will do is I will use 0.15 and 2 in 10, 9, 5, 4, 3, 2, 1. So I will do small r over d 0.15. D over d is 2, as one of the students told us. Keep going up, keep going up, keep going up. Stop. It cuts the d over d equal to 2 line here. Then keep on going horizontal. 1.3. Hello, Ahmed, how are you? So now I will, what happened to our whiteboard? Oh, come on. Yes. So I will use K equal to 1.3. Okay, we can put a little small value just to be on the safe side, but yeah, in an exam setting, write 1.3 to 1.33, whatever. So now, done. Finish the problem.
Hocam, should we use the higher value to be on the safe side? Because if it's higher, means it can carry more stress. So in order to be on the safe side, we should take the higher K value. Because K is at that is going to increase our stress. Isn't it?
Probably I need to think T average is equal to T allowable over K. If he's saying K value is higher, then I will predict lower average stress.
But higher allowable stress.
Okay, let's now put 1.3 or 1.32. We will think about it, but that's a good question. But I think that K value small will give me more room. Oh, okay. We something to think about for now. Okay, I will put a star here that we have to little bit think whether we want to overestimate or underestimate. Okay, it's a nice question, by the way. Okay, finish the question for me. What should I do now? Anyone?
We have found the K value, we know the allowable stress, we will find the average.
How do we find the average shear stress? Anyone quickly?
We know the allowable, we know the.
Allowable shear divided by 4.
Okay. But the question says that I have to find the maximum power. So,
Rates.
so what I will do is,
That will be the power.
very good. So what I will do is I will say it is 1.3 equal to 8 multiplied by 1000. Then we have pound per square inch divided by average shear stress, and that will give me an average shear stress value of I don't know how much, something around 6,000. No,
6,660.
really?
Our fund 162.5.
162.5, let's say. Okay, now that you have
You can say that PSR hocam. Instead of that PSR.
Hmm?
Instead of saying PSR, we can say 6.2 PSR.
Good. Yes, of course. 6.16. Very good. I agree with you. Pound per square inch. Okay, everyone. Now give me. The question says you have to give me the maximum power. So maximum power is equal to, give me tau multiplied by omega. Then I have power equal to torque multiplied by omega, which is 900 multiplied by rotations means 2 pi radian per minute means 60 seconds. RAD. Okay, I think it makes sense. Then done. Hang
I
on.
have another question.
Uh,
It says find the maximum power. So if we use the T average, we're going to find the average power.
oh, no.
Isn't it?
No. I will tell you why. No. You're not getting the point. Actually, what happens is that, hang on. What happens is that the average shear stress value actually uses this linear kind of a behavior. So these individual lines, they are taken into account. Life is beautiful. But in an original where you have sudden change in the dia, you have a behavior in which these individual stress lines, one of them far more exceeds this line. You can even see the diagram that I have created. So if you just use average shear stress is equal to TR over IP, and using that you get hold of the torque, then you will end up making an object in which you will have a stress line like a red line, this one, that will exceed and your system can fail. That's why you are using this K value, so you remain within the allowable value, and then you can predict the power.
I understand.
Are you sure?
Yes. I
Because
understand.
it's the individual lines that exceeds my average estimation, and I am scared that the individual stress line exceeds and it will just put the system into failure. Okay, how do I proceed now?
Could you repeat my friend's question again?
Okay, I will repeat. You know, the problem lies in the fact that if you use shear stress is equal to TR over IP, and you predict average shear stress, and then whatever that average shear stress is, you came up with a value, and I ask you that the object will yield at a maximum value of some other thing, and all of us are very happy, you know, my maximum shear stress that the object can sustain at some maximum torque, you know what, it is within the allowable value. I'm so happy. Turns out that this maximum shear stress that you keep on predicting is actually using this behavior. When you have a sudden change in the dia because of the stress concentration, one individual stress line is way more than what you have been predicting through this simple formula. So what you are predicting is fine, but one individual, because this is average. one individual line will exceed and your system will fail. So in order to take into account that one line that is exceeding the average value, you have to use that k value. So for example, if there is one student sitting in this class who is just a genius, right? For the average class, I will keep on proceeding, right? But I will keep on leaving that one genius guy at a time. So in order to take into account him, I will have to take some bias. You get my point? So there is one stress line just completely exceeds this estimation. Okay. I'm not sure how much this is clear, but we talked about it last time as well, no? Okay, gentlemen, ladies and gentlemen, let's proceed. So I will have, hang on, 6-1. Please bear with me, 6-1. What was the value? 616? 6-1? 6.
6153.84.
6153.84 equal to TC. Then I have over polar moment of inertia, J or IP, whatever you have been saying, 6153. So I will make the correction here, 6153 point whatever, 0.84 is fine. Now I have to use the torque, then C. Now between the two of them, should I take the dia of AB or BC?
Small one.
The small one, because that is more, that will give me more shear stress or a better estimation for that matter. So I will take the small one, not the big one. And I will write 6153.84 equal to T multiplied by, do the number crunching. I'm coming to your desk. Then do the number crunching. I'm coming to the desk to double check. This gives me in kilo pound inches, and power comes out to be TBC multiplied by 94.26, which gives me some value in inch, pound inch per second. And okay, hang on for a second. Please bear with me. And then I will write 1 horsepower. Again, this is very confusing, I know, is equal to 550 foot-pound. And you need to give me the answer in horsepower. Do it.
For the J value, we use the inner diameter, the one that is smaller,
No, of course.
3.75.
The smaller one. So it's the extension of the same stuff that we had been doing, right? You remember that we had a hole in a simple plate. We talked about stress concentration. The dimension suddenly changed. We talked about stress concentration.
Hocam, the first moment of inertia was P over 2 times C, the radius sport power, right?
You mean the polar moment of inertia? That is, I will give you the formula. J is equal to pi by 2
Times P over
C.
4.
I think so, huh? And where C is the radius. Yeah,
Could you repeat previous slide?
absolutely. Absolutely. Yeah, please. Because my point is that every shear stress that you are finding using PR or IP, that gives me an average estimate. Exactly like for the class, the average comes out to be 65.
But there's somebody sitting who has a score of 95, who is completely out there, upright. I have to take into account him. So this KI view gives me that kind of compensation where I also take into account that one individual student that is sitting up there, one individual line that is exceeding my expectation of that average shear stress. That's why that is.
For that, we need to, for the trying to maximum power, we are counting the average shear stress.
Oh, no, I will answer it separately. So this is linear line, right? But if I have to account that red line, that red line will be way more than, so it will be somewhere here, more than this black line. That red line, you see that red line?
Yes, we
That will be here somewhere, here. So I am scared that I will keep on talking about the average stress. But it will leave that little chunk that is out there. So that's why when dividing by 3, it gives me little, or dividing or whatever I'm doing. It will take into account that, take into account that.
Okay.
So just,
So why are we choosing smaller?
again, it's, I have to go for a safety estimate.
The
The
bigger one,
the smaller one will give me the right estimate, right? Last time when we were covering similar topic, one of the students said, does it depend on from where we cut? I said, no. Then you have to talk about stress concentration, you go for the smaller dimension.
Smaller.
Somebody said.
So what was the most powerful?
Okay, let's finish this. Okay, everyone, we have to finish this because I think I have given you time. Done. Okay, so let me finish the question quickly. This gives me 33.75 divided by 2. This gives me pi by 2. Then it gives me 3.75 divided by 2. Correct? Then it gives me power 4. Then this gives me 64. Then this gives me 6 into 10 power. Anyone who did it? Okay. And then this gives me 910 horsepower. Done. Good. Is there anyone who
What's C?
radius? Radius.
It's 9 divided by 16, right?
9 by 16 is
Smaller.
no. That is the fillet. Okay. No. That is the fillet. Radius of okay. As long as you understand, I'm happy. 654321. Let me ask very quickly. Dogukan, Abu, Tanish, Tashan Shan, Uze, Aisha. Should I proceed? Okay. Now we have chat message from yes. Okay. So we have very quickly do this problem. We will do it at sonic speeds. Again, I have a circular shaft. Then we have I understand the confusion because when we talk about average shear stress, you are like, that's average. Why not maximum? You are talking about the maximum actually, because if you use this formula, actually you have equal to T R over IP, right? So what is this C value? This C value is the radius, the maximum distance from the center. So technically this average shear stress is giving you the value for maximum average shear stress, that is this black line. My contention is that there is actually, because of stress concentration, a line that is this big and you are underestimating. So anyways, okay, quickly, now I have this A, torque, then I have B, and by the way, you are doing it. Then I have nice and beautiful pink line like this. This is 700 pound-inches. Then I have 500 pound-inches. Let me use an orange one. Nice and beautiful, 500 pound-inches. Then I have a nice and beautiful, the shaft has a change in the dia. This is one continuous shaft. Life is beautiful. Then I have hang in there with me. Then I have dia, a torque of 1500 pound-inches. 1500. Is it visible, everyone? Okay. Then I have, oh, come on. There is another one. Come on, 300. 300. That's just insane. Too many of them. So I will just put it very close to this one. Come on. Yes. 300 pound-inches. Okay. And the radius is 0.05 inches. Again, the radius of fillet. Please don't make that mistake. One of the students made this mistake. I urge you not to make this mistake. So radius of fillet is 0.05 inches. Then I have dia is 1.25 inches, and oh, come on, where is the dia? 1.25 inches. 1 inches, ha, ठीक है, 1.25 and 1 inch. So this is 1.25 and this is 1 inch. You do the problem yourself. 1 inch. Use your imagination.
What's the question?
Yeah, that's the question is that you have to find the maximum. Find the maximum shear stress find the maximum shear stress. This is C, maximum shear stress. This is the question. Find the maximum expected. Again, I think this is just English. Okay.
Is there an allowable version that you're going to give us?
Sir?
Allowable stress in the.
No, I'm not giving you the allowable. Just give me the maximum expected shear stress. So just use TR over IP formulas and give me the maximum expected shear stress. I will be opening that chart as well for you. I should have brought that, by the way.
Sir, what is the 0.05?
That's the fillet. It's not that sharp. This thing is not that sharp. There is a slight 0.05 inch of fillet, and do not confuse that with small dia. By the way, we had.
Sir, for the previous question, can you give me the answer? Final answer.
Yeah, why not? I gave the final answer. 6 into 10 power 6 pound-inches per second. Did you get this?
I was confused about the radius. Which radius to use in 2 pi r? The bigger.
2 pi r?
This converting RPM, 900 revolutions per minute. Am I not going to convert this 900?
When you're converting the RPM, so 2 pi r? No, that is radian. That's not r. When you insert, you have to write 2 pi RAD. There is no radius here. So when I have something in RPM, I want to convert it into radius per second. I multiply RPM with 2 pi divided by 60. Okay, and it gives me the answer in radian per second. You don't have any multiplication of r. Okay. Things fine. So I will do the question with you. This is not an easy one, by the way. So first of all, most of the students are like, come on, where should we even find it? And this question is not easy. So you have to proceed step by step and march along. Shear stress AB equal to T AB, C AB, I AB. Oh, sorry. TR over IP. I apologize. IP or J if you want to use. Whatever. As long as you know that this polar moment of inertia, I am happy. Oh, and then you will say that when you make a nice and beautiful cut, you will have TAB plus 700 pound inches. Now I'm answering your question. Yes. So you see, I am making a cut, what we were discussing before the class, and I'm throwing this chunk away. So TAB plus 700 equal to 0. And we have TAB equal to minus 700 pound inches. Boom. Now we have students who are saying, like, come on, what about if I use TBC? Okay, we had a student who is who actually I think wants me to tell clockwise or anti-clockwise. So it is clockwise. Good. He's right. Then we have TBC over CBC over JBC. Again, you get stuck here. What about TBC? Again, I'm answering your question. You make a cut. Yes, ABC. You make a cut, you throw this chunk away, and then you follow the same drill of looking from this side. And if you have any student who is confused, you have to stop me. TBC plus 700 pound inches plus 500 pound inches equal to 0. For those of you who are wondering, why are we doing all of this? Look, they asked us to give them the maximum shear stress. You don't know where does it even happen. So you have to find every single possible of them. So we have TBC equal to minus 1200 pound inches. And we had a student who wanted me to tell you clockwise or anti-clockwise. So clockwise, right? Clockwise. Yes. So we have minus 100. Now T, this is confusing now. I think I made a mistake. A, B, C. Unfortunately, we have another one of these fellows. So why don't we make a D? How many agree and how many disagree? Let us make a point D here as well, everyone. Otherwise, it's very hard. Now let's talk about CD. So TCD is equal to hang in there with me, hang in there. 700. Okay, so it is equal to T CCD over JCD. This is going to be confusing. Now TCD is equal to, again, make a cut after C, and this green one is right next to this step, right? I'm not even sure whether the camera is on. So this green one is pretty much right next to it. So now I will have TCD plus 700 plus 500, and that's it, or anything else? Plus 300. Good. We have a good comment from students. Plus 300 equal to 0. Yeah, you have to ask me what happened. We have a student who is asking a question. Me. So you have TOS CD equal to 1500. How many agree? How many disagree? And I will put a clockwise here, nice and beautiful. Excuse me. Hmm? 0.61. Okay, so now finish this question. You will finish this question by saying, do the number crunching. Tau AB is equal to, we have minus 700 pound inches multiplied by CAB is 1.25 inches over, and I will use nice and beautiful purple color. JAB is pi by 2. Oh, come on. 1.25 is wrong, no?
Yeah.
Wrong?
0.7.
Sorry. Okay, this was not good. 1.25 divided by 2 inches. So easy to make a mistake here. JAB is pi by 2. Then I have 1.25 divided by 2 power 4, inch power 4. Give me the answer quickly.
Hocam, is the final maximum stress is 16.8 psi?
With the K factor or without K?
With the K factor.
It's 9367.
9.3.
What did you say?
I found 16.8.
9367 is in my notes, but we can double check together. Okay, what is shear stress AB? Anyways, you can find it.
The answer is 1825.
23 is in my notes. Thank you. Pound, inches, or 25, whatever. We have a chat message from Abu Bakr says 1825. I agree. Good. 1825. You can correct this. And then I have.
And also minus.
Yes, yes. Okay. So you can put a clockwise here or negative. Good. Okay. Then we have torque BC gives me. Oh, come on. This one. Shear stress is the units. Pound per square inch, right? Good. Thank you. You are right and I'm wrong. I appreciate it. Pound per square inch. Okay, then you have torque shear stress BC is 3125. Can you please double check yourself now? Anyone? And CD comes out to be TCD is anyone who can tell us minus 1500 pound inches. Then I have radius is, I don't know what was the radius. So many tabs of Zoom. What was the radius? 1 divided by 2.5. Okay. Divided by polar moment of inertia pi by 2.5 divided by, very easy to make a mistake here. Using 0.05, this is fillet radius, please. Then shear stress CD is
7,000.
Good. 7,653. Double check yourself. Boom. Can anyone please double check this one because I'm just writing it. Good. Okay. Are you with me? Everyone positive? Everyone is with me?
It's also PSI, right?
Yeah. Okay. I actually very quickly have been just writing. Sorry. Okay, everyone, fantastic. Then
finding the shear stress, we using the reaction one, right?
नहीं,
But
no. हाँ, reaction one.
reaction one, right? Because we use -70 liberal.
Oh, so you want me to put minus sign?
All of them will get minus.
Minus. Good. So, yeah, sorry.
Can I ask something else?
Oh, why not?
Why do we 0.5 inches on the shear stress of CD?
Oh, because CD has 1 inch of dia, whereas AB, this shaft has a dia of 1.25. So I use 1.25. Oh, yeah. Okay, so everyone, thanks for the patience. I appreciate it. 5, 4, 3, 2, 1. Now give me R over D and D over D.
D over D is equal to 1.25. R over D is equal to 0.05.
R over D is 0.05.
Yes, because the small d is 1 and the R is 0.05. So
Okay. I think he's right. So I will go back and just for the sake of double checking, I will hang on for a second. R over small d 0.05 over small d. He said 0.05. Good. Capital D is 1.25. Small d is 1. So I think he's again right. Very nice. 6, 5, 4, 3, 2, 1. So I have R over D as 0.05. I will go here. And capital D over small d is 1.25. And I arrive at this curve. It cuts it here. I will go left and I'm getting 1.53 or 1.55. Very good. 1.53. And R over D is 0.05. D over D is 1. Yes.
from the chart that I've checked out from the internet, the charts that you are using and the chart on the internet is different.
Really? How much? But again, these are developed empirically, but they shouldn't be too much different.
There's a lot of difference. It says 2.2 in here.
Oh.
0.05.
Okay, I might want to have a look at this. Yeah, that's you know, I really want to say my defense and okay, why don't you double check from here? Geometric stress constant in a shaft with shoulder fillet. Yeah, this one is in axial tension. This is the chart you are seeing, right? It says axial tension.
So
Got it?
Yeah.
Good. So I need to answer his question. He has a very good question. He's also saw a stress concentration chart from the internet, pretty much the same, but it is for axial tension. What we are going through right now is torsion, the torque. I forgot his name, if you can. So his question is similar chart, entirely different K values. That was for axial tension. We are talking about the torsion effects here. So remember these things.
Yeah.
Okay, everyone, life is good. So K is equal to allowable divided by average. Again, very misleading, this average shear stress that average with a little max, with a little small max here, because you are using radii. So which one should I use? Should I the one I find maximum, and I think 1823 no, 1500 no.
7,060.
CD, good. 7653. So boom, 7653. T allowable is my T max. So it is T max divided by this is. Oh, why am I using 6122 here? Yeah, probably I made a mistake. Anyways, so yeah, I will just correct myself. 7, sorry, 7653. And this value is equal to 1.53, and tau max at this CD comes out to be, or C if you want to call it, right at the edge. Um, 936. Okay, whatever the value is. $1,200.
For example, K value is 1.5.
Nee, 1 minute. Oh, sorry, 1 minute. Did we calculate? There is a mistake. There is a mistake. Give me 1 minute. What is the? This is shear stress BC.
So don't we have to add the stresses together? I'm not
This
really
is
sure. Why are we using the only?
torque. I will answer. Okay, this is. Can you please give me the answer for this one by using 1200? I think this is wrong. Anyone who can use a calculator quickly? Anyone who is doing it, please. You genuinely need to do it. I need them.
It's 3,129.
Really? No, shouldn't be. So this is 1200. This is 0.5 divided by pi by 2, 0.5 power 4.
That's not
It is
0.5.
not, it is not 0.5, it's point.
0.675.
Yeah.
Because the diameter is 1.5
1.25 divided by 2.
Okay. Torque BC. Okay. I think there is a mistake here. Probably next time I will explain. I think there is a mistake because when I cut from here, I have shear stress BC. Then because there is my concern is that there is this step here and there is a C. Okay, I think I have C. Okay, and please give me 1 second. BC. Let's find it one more time. Okay, let's call it as TC equal to, hang in there with me, is equal to 1200. This time use 0.5 divided by, I will explain. Give me 1 second. Pi by 2, 0.5 power 4. And we have average C equal to 6122 PSI. Why? Because if you cut it right very near to this one, right before this one, you will have to use this radius. Okay, and here I will be using this value 6122.
100.
Yeah. So for those students who are saying what on earth just happened, let me try to explain. The problem is that you have a stress concentration here, right? When you have a stress concentration here, I cannot just cut from any place and take that torque. I have to take the torque right, or I have to talk about the shear stress right next to this layer. Are you getting my point? So that's why in any case, if you are putting a torque here, it will have a finite distance from here. It cannot be glued to this one. Let us say like this. So that's why I took a knife and I made a cut. But when I'm making a cut, I made a cut right before this one. So I intentionally included this radius. So that's why you see I got hold of this value and I'm utilizing this one, and this gives me the right value. Okay, let me see our students. That's why I explained. So probably if you want, you can divide this into A, B, C, and probably a C prime if you want, with distinguishing the C and C prime and then proceeding, or you can follow this strategy.
But the 7,000 is bigger than 6,000.
I know. But here comes my concern. Let us say by cutting at another portion, I get even a more shear stress or more torque, but that's not the point, right? I have to get the torque right, which is happening near or right at the stress concentration. Just finding the maximum torque or maximum average shear stress is not the concern. So when I am cutting from here, let's say, and I'm getting a shear stress of 1823, just imagine if I had got 10,000. I wouldn't have used this 10,000 because this AB concerns here, whereas my stress concentration is happening on this region. So I have to, are you getting my point? I have to get hold of every shear stress for this region.
But the question doesn't ask for the maximum shear stress in the stress concentration region.
Got it. I will tell you. I understand your question. But the point is, look at this answer, 9367, right?
Yes.
But is 1823 greater than 9367? No. I will not have any value here that is greater than 9367. If, for example, I had got a value of 10,000 here, right? Then even after calculating 9367, we still would have said, maximum shear stress happens there, 10,000, life is good. But if you want to use the K value, you have to use the K value right where the change is happening. And for me, I have to get the torque exactly at that layer. That's why I corrected myself. I used T, then R over IP.
So it was pointless to find the other stress then.
Pretty much. But then from the beginning, none of us actually knew that it will turn out to be like this. For example, just imagine.
We need the shear stress of C, right? That's what we try to.
Eventually, but we could have changed the question. For example, I could have come up with values where, as I gave him an example, you got 10,000 here. Then even using K, if you are getting 9367, still your answer would be that 10,000.
Because we have to find at that point.
So I think let me correct this a little bit because I am scared that everyone will get confused. So I will put a C prime here right after C. So let's say C prime is right where this green arrow is happening, and C is right this point. Okay, C and C prime are different. And let's say you put a prime here and you put a prime here. Let's say T CD prime, C prime D. Let's say, just to be clear, this is C prime D, and this one is control Z. Let's say C prime. This is C prime, and this is C prime. Okay, and this is right. So, last semester as well, when I was going through this problem. I exactly stopped at this point. I don't think if this is clear. No, it's not clear.
So for this kind of questions,
Oh, yeah.
we need to look at the dimension changing part, because this part
Yeah.
makes the answers our questions. What
Hmm.
is the biggest stress?
Stress concentration. Stress concentration will happen where you have a sudden change in the rise. So this is the point of concentration. All of us try to squeeze through this door. This is the limiting
The
portion.
value cannot exceed the maximum one. because-
Should not. Should not. We are scared. Okay.
But hocam, when the AB part exceeding the C prime part,
Hmm.
does it affect the C prime part? Along, for example, in AB part, along
Got it. If your question is if this becomes 10,000, let's say you are getting 10,000 here, and at the end of the day in an exam setting, the values are like that for the talks that you are getting a 7,500 here, right? Then for me, worrying about this is pointless. I have something bigger happening somewhere else.
so why we are looking at that part?
You're not getting my point. My point is that right from the beginning, I didn't know that this will come out to be this. So I had to go through the whole process. I think this is not clear. Should I repeat or should I continue? Should I repeat? Sure. Is this clear? Why did I name them C and C prime? Because this green one was happening right after this, right? Definitely half a millimeter, but at a finer distance after it, right? So just imagine if it is happening half a millimeter, 300 pound inch to the right. I take a knife, I still have that half millimeter, right? Hang on. So I will use a knife and I will get that 0.5 inches. And that's why I use that to get hold of this C prime D. Okay. And similarly, you can get this is C prime. So yeah, I'm not putting my knife through it. I'm putting my knife through this one because again, I used this 700 plus 500 plus 300. Yeah, so C prime D means for sure my knife is going through this. Anyways,
We use one, we use 1200,
huh?
but we use 1200.
We use 12 what?
We use 1200.
In the BC, right?
Mhm.
Okay, because when I made a cut from here and throw this chunk away, I got 700 plus 500 sitting here.
No, just after the diameter change.
Okay, just after the diameter change, C prime I never calculated. No, this is point C. This is point C prime. So I used C prime D. So let us go back. Yeah, I used exactly. He's right. So this is 1200. Yes. So I used the knife. I made a cut right through it. I threw this chunk away. And as one of the students said, you are using 1200. Yes, I am. So where am I using it? I'm using it here.
It's positive because it's the
So
reaction.
let's call it as, thank you. What is your name? Very good. He's right. C prime. Very nice. Thank you. Excellent. His remark is let's put C prime here. I appreciate it. Very good. C prime. So used a knife to make a cut at C prime. C prime, right here, right here, right here, right here, right here, right here, right here. Okay, and that's what I used here. So average CC prime, average CC prime. Here you will put average CC prime. You can put CC prime. Thank you. Okay. And you can make a remark here. TCC prime is equal to 1200 pound inches. Thank you. So we have TCC prime plus 700 plus 500 pound inches is equal to 0. Okay. CC prime, okay? Should I proceed now? Should I proceed, right? So I kept on using the knife between AB, between BC, between CC prime, between C prime and D. Right? Okay. Okay, before I proceed, Hassan, okay, Hassan just joined. Dogo Khan, Ebu, Kashan Chan, Uze, Aisha. Is it clear now? Can you please confirm? No? I hope. So left and right, we have arrived at. Just a second, Hocham. Okay. Okay. You want a break?
Yes.
Okay. We can have. Actually, I will take some time then to make some drawings. Okay. How much? 5?
Times 2, please.
Okay, have a 5 minutes break, no? You can have a 10 minutes break. That's fine. 11:54. Yeah, we went left and right, but I think we arrived. Yeah, exactly this happened last semester. Exactly. Like I'm just baffled that exactly like this. Then I put C prime, then I changed the question, then I made a prediction. Yes.
I found another chart.
Should be a little different.
No, this one, it uses the actual torsion and the is dog change.
So they are the same as our chart?
Yeah. No, they are not.
They are closer to our chart or very different?
They're like, look at it. In this part, approach.
Oh, it's the same thing that you showed me.
And also there are other things like that. In here, they put the formula. There are other charts as well, like, for example,
Let me tell you one thing. So you will find
many charts.
changes because these are empirical. These are experimental. One scientist performs or one group of researchers perform experiment. Let me tell you something. You went through fluid mechanics, right?
No, but I
And
know.
from fluid mechanics, they covered
Viscous boundary relation.
good. And they covered heat transfer. In heat transfer, they talk about circular cylinders and heat loss from them. I still remember even there you have formulas somebody developed in 1930s. It's a certain relation in 1970s, the formula gets improved. 1980s, 90s, it's very accurate. So these are empirical relations we have, and empirical charts and relations, you will find a little bit of variations. That's why the word expected. These are predictions. We are just using allowable values and these K values to have a certain sort of, expectation, prediction. So I'm not surprised if you are getting a chart that is a little different than ours. But for an exam, you will all have one chart.
This will be provided.
Of course, I will be providing. Yes.
Hocam, yesterday I said that.
I did not change it.
No, hocam, could you change?
Oh, I will change it right now. So let us change it. Yeah, left and right, and we have arrived at in order for me to have this relation of the average shear stress work perfectly in this region, I have to use a K value.
Yes. Mhm.
because only the K value will tell me, you know what, actually here you have a non-linear profile, let's say like this, something,
Exponential or
Ah.
something like that.
non-linear. And you know what, now the K value will make sure that this chunk is within the limit.
Okay, so K value is like a safety factor, right?
Let me put it in very simple terms. Look, so for example, previously I was putting a torque of 20 Newton meter. Let's say previously simple shaft, very small value. I'm giving you an example, 20 Newton meter. I was happy. I'm within the safe limit. We are happy. Then suddenly for the same shaft, there was a change in the dia. Then I kept on saying we can still use a torque of 20 Newton meter, and that shaft, let's say, breaks. This is a very hypothetical example. And I'm like, oh, come on. Just because I had a step, I still use the same 20 Newton meter of torque. Why did it break? Then one of you will tell me that now there is a step. So, this shaft is more prone to, yielding or whatever. Why? Because technically closer to that step, the one line of shear stress was way more than what I had been predicting through every shear stress. So that's what I have been trying to tell you, that now I am not allowed to use a 20 Newton meter of torque anymore.
Okay.
So now what torque I will be using? Probably 12, probably 15, probably 11. And who would tell me that I have to use a smaller torque? The K value. Now the K value, when you incorporate, will give you a smaller value of, will give a smaller value of, will give me a smaller value of T.
T value. Okay.
And I will be careful.
Okay, it will be max. Okay.
Does it make sense?
Yes.
So go through that approach. You had a simple shaft, you were using 20 Newton meter of torque, you were happy. Now you had another shaft, the same size, but now this time a step. The shaft breaks, you're wondering, then you realize that you had to use the K value because closer to that step, you had one individual stress line that exceeded way more what you were predicting through TR over IP. Okay, 6543.
What if we do not have this?
If we didn't have fillets, if you have
Very sharp edge.
very sharp edge, then it is so much prone to,
Even higher, right?
oh, it is so much prone to,
Break. But what if I want to calculate the exact value of how much, let's say, shear stress that's
K value, you mean?
line?
You mean K value?
Yeah.
So for example, if
Where R is 0.
then what is the K value? That's your question.
It's infinity.
Indeterminate. There is something indeterminacy. You cannot predict. You are in the unknown zone. It's more like indeterminacy of point. Extremely sharp edge, and even the paper breaks. So we will not go to that. Like in fact, even if you make something R equal to 0 is everything will have even a non-zero fillet. I think the break has gone really long. Okay, 654321. Okay, I think we should start. There is a derivation that we have to go through. I think we should not skip all the derivations. So what I will do is I will go through Google Drive. You will. Okay. So I will go to. Okay, so I think derivation I will not skip this time, but we will go through the derivation very quickly. Okay, so instead of writing everything, I will just go over it more like a presentation, if it's fine with all of you. Not sure how many
really want me to go through derivation slowly. But if I completely skip the derivation, I think it will be wrong. So please bear with me. I will just use some. Oh, 2, 3, huh? 3. This one I will copy paste. And because we cannot skip all the derivations, like, come on. And remember, this is what I really went rather slowly last time, but I think derivations we can go through. Okay, so we are actually coming to the one of the most important topics of your strength of material. So bear with me, derivation, I will just skim over and I will go through the results in detail, of course. Okay, so 6, 5, 4, 3, 2, 1. Okay, so we are talking about now what we call as beams. So what we will talk about is, of course, this is your nice and beautiful beam. I'm sure in statics they went over this, right? Right?
Yeah.
I'm sure they did. So you have nice and beautiful beam. Okay. Okay. Nice and beautiful, simply supported beam, let's say. Now, the kind of beams we will be talking about, we will say that they are symmetric with respect to the y-axis. So for example, if I have this beam, I will be talking about such kind of a beam that is symmetric about the y-axis. I hope it is clear. So I can talk about this rectangular beam and it is subjected to a load like this. Okay. And again, the loading will be also will be going right through, let's say, the center. Similarly, I will be talking about this beam, let's say. Again, you can extend it here. Nice and beautiful. It is symmetric about the y-axis, right? I can also talk about the triangular structure, right? Again, you can extend it here. And for this beam, for example, it is subjected to a load like this. I will not be talking about this beam. So you need to know the constraints of our information. I won't be talking about this one, okay? This can also be a beam, right? It can also take loads, but I won't be talking about this one. Why? Because it is not symmetric about the y-axis. If you want to talk about, probably in 434.
If you turn this,
Sorry?
if you turn this,
If we turn?
90 degrees.
Ha. Good. Excellent question. Very nice. So if you turn this, excellent question. Very good. Now I can talk about this in 206, okay? Because it is symmetric about the y-axis. Agreed? Okay. Another thing that I am talking about right now is straight load. In this class for 206 right now, in the initial 2-3 classes or 4 classes, I won't be talking about a situation in which you have load that are acting at an angle. So I am talking about nice and beautiful straight loads for a beam, nice and beautiful, symmetric about the y-axis. Two things need to be clear. Okay. So you understand the constraints of our next 3 classes. By the way, that was an excellent question. Yes, okay. Here comes the derivation. Bear with me. So what we will be talking about is nice and beautiful beam Okay, simply support it from here. Okay, I have a roller here. Load is acting right through the center. When the load is acting right through the center, you know how to make those bending moment diagrams, right? From statics. Bending moment diagrams. Okay, so I'm skipping that for now. You can use that statics principle, bending moment diagrams and shear force diagrams just to know where does the maximum bending maximum moment acts on that beam. That's fine. But our concern is once I have found that maximum bending moment, then I slice it and then I want to talk about which section at that point is absorbing or holding or sustaining the maximum stress. So that's what we are talking about. I will go through my statics. I will find out maximum bending moment. At this point, good. Then I will take a knife, I will cut it, and I want to talk about whether the top point has the maximum stress or the bottom point or which point. Number one. Number two, look at this beam right now. A load is being applied. All of us agree it will bend, right? It will bend. Now, when it bends, all I will do is I will say that the top portion is under compression, right? How many agree? And the bottom portion is in expansion, right? And the bottom portion is in expansion, right? Okay. Now, between these two, there will lie a portion that is neither expanding nor is compressing. And we will call this portion as our neutral axis. So this portion is compressing, this portion is compressing, this is compressing, 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 but there is a fiber here that is neither compressing nor is expanding, and I will call this fiber as my neutral axis. Okay, now where does this neutral axis lie? Again, we will need to find where does it lie. So just remember that I am looking at this beam from here. I know it's bending. I know the top fibers are in compression. The bottom fibers are in expansion. So I will say fiber which is neither expanding nor contracting. That fiber is neutral axis. Neutral axis is where bending is 0. Okay, look at here. Okay, this pen I borrowed from one of the students, so I won't use this one. Let's say this one. You see, now what is happening is that the top surface right now is for this fellow that I'm holding. Can you see me, by the way, online students?
Yes, hocam.
Sure. Okay. Now I think now they can see me. How can I pin my, okay, this is pinned. Okay, I'm getting better in Zoom. So you see, I am putting a load like this. The top surface is expanding, right? How are the fibers behaving? They are expanding. So stress actually is flowing in this direction, right? Like this, like this, like this. Stress is flowing. For the bottom one, this is definitely going to break. It's not good. Yeah, no, this is getting recorded. I don't think the university will be impressed. So you see, yeah, like I'm serious. So yeah, okay. Anyways, so look at the bottom fibers. They are getting contracted. So stress is flowing in this direction. Remember this. Stress is flowing in this direction.
You mean the shear stress?
No, that's what I'm trying to explain to you. No, this is very important. Good question. Right now, I'm talking about the fact that stress is flowing in this direction, and I am still talking about the normal stress.
Normal stress. Okay.
Excellent question. This is can be.
You know, the shear stress is outside in the edge of the body. You know, when pretending to got this section of
Good.
our time.
You are actually right. Good. Excellent. Actually, when you are cutting it, there will be a shear stress in this direction. There will be a shear stress in this direction as well. You are right. I understand that. But right now, because of bending, I'm talking about a normal stress. You are actually right. But I'm talking about a normal stress. Very good, by the way. Now that you're clear that this is a normal stress I'm talking about, then I will have, let's say, strain. So strain will be, let's talk about a fiber, the green one, that is a little on top of this red one, right? So what about the strain in this fiber? Everyone will tell me the change in length in this fiber divided by the original length. So what is the change in length of this fiber? That is, I'm going y above the neutral axis. So it will be rho minus y delta theta. Now delta theta is how much this object is going like this. Minus rho delta theta. What is rho delta theta? It is your original length, right? Because change in length means length of this fiber minus the original length. And what is the original length? Original length is this fiber because it is neither expanding nor contracting, right? I told you the neutral axis is which does not have any bending. So technically, this fiber is not expanding. This fiber is not contracting. So rho minus by delta theta minus rho delta theta. Change in length divided by original length is again this fiber. What is the length of this fiber? It is again rho, that is this blue line, which is your radius of curvature, delta theta. S is equal to r theta. So change in length divided by original length gives me the strain. So I get the strain in this fiber as, again, I will use limit delta theta equal to 0. I will get rho minus y minus this rho divided by rho. I will get minus y over rho. Now, I know that stress over strain is equal to elastic modulus. I have got the value of strain. I will find the value of stress. So this is again a derivation. We are just going through it. Now comes the important bit. I have got the formula for maximum stress, but the problem is I really hate this radius of curvature. Like, come on, how can I just find radius of curvature? Usually in my life, I have to replace this radius of curvature. So what I will do is I will say summation of forces in the x direction is equal to 0. Of course, the object is in equilibrium. In fact, the object is in static equilibrium. I will say integral stress x dA equal to 0. So you see, hang on, please focus. I'm bending this, right? Because this is a beam. I put a load. This object is under bending, or it is being bent like this. Either way, I have told you that the stress flows like this in the x direction, right? Stress flows in the x direction, right? Okay. So if I ask you what is the force that this object is subjected to, you will tell me that the stress is acting in the x direction, multiply by this area, right? So stress x multiply by this area will give us the force that is being flown into the x direction. So this is.
That means you said the area according to y-axis and the stress is according to x-axis. So when we each as a mathematical expression and can we say how should I say this area times stress times each times sine theta or cosine theta.
You are very close. I agree with you actually, because Yes, good, because
I'm so trying to think, it's the type of product, for this one.
so for example, I understand your question that the stress is acting in flowing like this. At the end of the day, the cross-sectional area is this. So I will multiply this stress with this area to get the force, because stress is force by area and force will be stress multiplied by area. So the stress is flowing in this direction, right? This is the cross-sectional area. I will look at like this and I will multiply the stress with the area to get the force. So in fact, cross-sectional area, excellent. So you can see there, I said in that orange box that I have, hang on, stress multiplied by area is the force in the x direction. Okay. So now all I have to do is summation. What happened? Oh, come on. Control Z. Okay, Control Z is not working. Anyways, oh, the paint is also acting funny actually. Anyways, so this integral stress x dA equal to 0, force is equal to stress into area is equal to 0. Now, instead of this stress x, I will substitute nice and beautiful expression that I found, minus E over rho y. What you can do is you can divide these two fellows. So the maximum stress will actually lie at the maximum distance from the neutral axis. And what is the maximum distance from the neutral axis? If this is my neutral axis, what is the maximum distance from the neutral axis? It is either the top surface or the bottom surface. Wow. So I substituted the stress x in terms of stress max. This is what I get. And then all I did is I equated this whole chunk to 0, because summation of forces is equal to 0. And immediately I'm getting this fellow, and I observe that integral y dA comes out to be 0. So what is integral y dA? First moment of area. Integral y dA equal to 0 means that the neutral axis will go through the centroid. Are you following me or not?
For the integration part, first we will do the y integration, and after that we will do the x integration, right? Because
No, I just said this is equal to 0. That's it. And integral y dA equal to 0 means that neutral axis will go through the centroid.
oh,
There's nothing. Yeah. Okay. Now that I have got this, the neutral axis will go through the centroid. The next part is do the summation of moment equal to 0. So you can even see this integral y dA equal to 0. This is what was taught to me, that y dash multiplied by integral dA equal to this one. That's how I concluded that the neutral axis must pass through the centroid. Okay. For summation of moment equal to 0, this time I have to be a little careful. So I will go back and just please have a look here. Look, just follow me. At the end of the day, you are putting a load here, right? So this object bends like this. If this object bends like this, then if this is the way the stress is flowing, right? Stress is flowing like this, or let's say like this, right? So all you have to do is, for doing the summation of moment, you will say moment that is being applied plus force multiplied by distance. Force multiplied by distance. What is force? This chunk. What is distance? This distance from the neutral axis. So force multiplied by distance plus the moment that you are applying, everything equal to 0. So in this way, you get nice and beautiful expression for M. You do one more step and you get this answer. So M comes out to be minus stress max over C. What is this one? Moment of inertia. So I get M is equal to
stress max equal to minus mc over I. This is the maximum distance from neutral axis, and stress comes out to be minus my over I. Now I know everyone is like, what on earth is happening? I will now summarize it. Number one, pure bending of beams. Stress is equal to minus my over I. Neutral axis goes through centroid. Please bear with me. Right now, I really need your attention. We have gone through the derivation. I cannot just skip all the derivations. You also have to understand my situation. Neutral axis goes through centroid. Okay, quickly, you are going to answer this. This is the beam. You tell me the XY axis that I am making. This is the beam. Tell me what is the coordinate system we have been following. This is my good. Very good. In fact, I was thinking this is Y. Okay, then what is my X? Good. X. Okay. What is my Z? Z. Good. Okay. I put the load. Okay, hang on. I put the load and the whole object bends, right? I will use a yellow color. Tell me the direction of normal stress. Tell me the direction of normal stress. In which direction? Be confident. X direction. Okay. Normal stress is in X direction. So what is the subscript of this fellow? X equal to minus my over I. What is the subscript of M? What is the subscript of moment?
Z.
Okay, Z. What is your answer? I'm putting the load like this. Like this. What is the direction of the moment? Which axis? Z. Yeah, Z. Okay. What is this Y? Distance from neutral axis. Don't use the word centroid. Although we have agreed it goes through the centroid, but you will not use the word centroid. You will use the word neutral axis. When the right time comes, you will know the reason. Y is the distance from the neutral axis. What is neutral axis, by the way?
The axis that doesn't change length when
And does not have any bending for that matter. Neutral axis is whose length does not change, which does not have a strain, which does not go through bending.
How was the moment in Z direction?
This is the Z direction towards you. Okay, I am putting the load like this. I lost the pen. Where is the pen now?
Pen is removed in front of you.
Yeah, this one. No. The pads pen. Okay, good. What about I? Anyone? X, Y, Z. You have to tell me. Moment of inertia.
It's on the Y direction.
Z.
See that?
Of course, because if I am. 1 minute. I think it's right. Hang on. Something as simple as this. If I am putting the structure like this, Z. We can think about it. So, yeah, Z. So I will answer your question like this. Look. If you're looking from here, if you're looking from the side view, how this object will bend? Correct, everyone? Yes. Correct, everyone? Okay.
Now just imagine its ability to resist this. For sure, which axis? It is which axis? Z, 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 Z. Done. Why the minus sign?
Because it's resisting to the torque that we, the power that we apply. So in order to be zero, the total amount of,
No. Think it like this. If your y is positive, your moment is positive. Think like this. So you are putting a moment like this. So let's say your moment is, let's say 20 Newton meter. Okay. 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 So 20 done. You are going above the neutral axis. Let's say 5 centimeter. Agreed? Okay. So just tell me, the fiber above the neutral axis will be in compression or will it be in tension?
Compression.
Compression?
Compression.
Everyone? So fiber above the neutral axis, when I am bending it like this, will be in compression. Everyone agrees? Okay. 5 by 100, good. Divided by moment of inertia is a positive value always. Good. I will put a negative sign here.
Because it's in compression.
I will tell you. The answer comes out to be negative. Agreed? That is what we were expecting. That's why the negative is in the formula. Let's do this drill one more time.
so negative will be positive, so it.
Good. So now I am talking about negative 5 centimeter. So this will be negative. The answer comes out to be positive. The part of the beam below the neutral axis for such kind of a moment is in tension. Makes sense. Let's do this drill one.
So it is really related to cross products question. What I mean is when we multiply minus time k times j, it gives plus r. So GGX represents positive.
Yeah, I think you are right. Then that is a great analogy. Yes, in fact, not even an analogy, you are right actually. Yes. If you think it like this, you are right. Excellent. Yeah. Good. Just before I say goodbye to you. Okay, so hang on. So big of a derivation. Just two things to remember. I'm talking about a structure in pure bending beam. It is symmetric about the y-axis. I'm talking about the load that is acting straight, not at an angle. The formula is minus my over I. Is this shear stress or normal stress? Normal stress. Got it? Before I say goodbye to you, why don't you answer a final question? Let us change this to, let's say, completely different problem now. I am putting a load like this now. So the beam becomes like this. Wow. So I'm putting the load from the bottom, right? So of course, this is not even practical right now, but it's a hypothetical case where I'm putting the load like this. So the object bends like this. So now tell me, the moment is, let's say 20 Newton meter again. Let's do number crunching. Now I have to talk about again 5 centimeter from neutral axis. Okay, what is the value of mz now?
Minus 20.
Minus 20. Are you following? So I will put minus 20 here. What about the distance y? Positive 5 by 100. What about Iz? A positive number. So stress will come out to be, oh wow, really? Yep, because if you're putting the object like this, the top surface is in expansion now. The every fiber above the neutral axis
is in expansion, so it makes sense.
Could we also solve this equation like this? Should I show you or should I?
Please. Why not? You can use a pen.
You can see the formula.
And then here, for here, for example, you can write it here. That's fine.
I should.
Or you can use a pen here, whatever you're comfortable.
Okay.
Huh?
Is it also like this is always in the middle?
Neutral axis. Neutral axis goes through the center. Okay, I will explain. I understand your question. Here, because this is the fact. You can write it here. You can write it here.
First, let me draw the x, y, z coordinates.
Okay. Still have 3 minutes. Please ask everyone. Okay, yes.
Now let's write the pure boundary equation.
Why? Instead of, good. Okay.
Seconds.
Because at first, it's like this. So when you use the right hand,
Good.
you
Yes.
put it as positive in brackets, but there's a negative because we derived it in the equation before. So now it's positive, it's negative, so it becomes
good.
a negative, negative, positive. Why is it negative in brackets? Because this time we are applying force from positive J direction. So when you use the right hand, again, it's going to be negative. This points in the direction of the wall.
So, but like activity forces, like this. So when you do like this, the fingers, the negative becomes showing behind. So because of the
That main equation comes from the derivation before. Sorry?
I think you're right. I think you're right. But I never thought like this actually.
Yeah, this in mathematical
That's fine.
expression.
Negative y. Why we calculate
And because you should show the areas according to
Yeah.
So I think you will arrive at the same conclusion. But you are right. Good. Yes. Good. It's the same thing.
yeah.
Same thing. Wow. Very nice. But we don't do this actually. But that's nice. Great. Yeah. Okay. Thank you. Okay. 1 minute. Just 1 minute. If you put y equal to 0, what is the stress that you get? Y equal to 0. 0. Makes sense? Makes sense. Where does the maximum stress lie from the maximum distance from the neutral axis? Good. And there was one student who asked this question, and I will say goodbye on that. Centroids. Somebody said something about centroid, right?
I asked about is neutral axis is always on the middle.
No. Thank you. Good. Excellent question. And on that note, we will say goodbye. If it's rectangle, it's in the middle. If it's
triangle, it's
1 minute.
one.
Circle, yeah, we will. Will we use that? Yeah, okay. Good. Middle. You are right. Very good. If it's like this, it will be in the middle. If it's in the circular, okay, yeah, it will be in the middle. Good. If it's triangle, no, not in the middle, right?
It's on the
B by 3. Good. I think everyone understands. So if you make a beam like this, you cannot say that your neutral axis is in the middle. For sure not. It will through the centroid. Okay, I think I have made my point. Stress X equal to minus My over Iz. That's the normal bending stress. Thank you. Well, we have to find it.
What's the landing?
Pure bending in beams. Normal stresses in bending.
So
You're
this
right.
notchless situation is the reason why we choose just symmetric to y-axis symmetry.
Actually, this is not very easy. For example, if your beam is not symmetric in the y-axis,
Mhm.
and you put the load right through the center, it will twist. If you have a C-section,
Yeah.
and just imagine you're using this for a bigger beam, you're subjecting it to a load it will twist. And now it will not be in only bending, it will be in torsion plus bending, and it will be more problems for us. So we would love to use something that is symmetric about the y-axis.
So I don't understand why when we apply force, why don't we calculate the stress in the X direction? You know, when you apply force, you know, let's say it's a beam like this, and there's a force applied, and it bends. Why is it stress in the X direction?
Oh, yeah.
Isn't it supposed to be in the Y direction? Because the force is coming from the Y.
Oh, if that is the shear stress, that good question, but
I was confused about that.
good question. So his question is,
Like, let's say,
So I understand.
let's say with the remote,
I understand the question.
when we apply force from this way, why is it?
I'm
stress
about
in
to,
the X?
I'm about to answer. When the load is acting from the top, you have a shear stress that is acting.
Uh-huh.
Right? But at the same time, this object is also bending.
Yes.
Because of that bending, you will have a bending stress that is normal to this surface, so it's flowing like this. So you have now normal stress, nice and beautiful. When you're putting a load like this, you have a shear stress, but actually you also have shear stress that is acting in the same direction as this one. We will talk about after 3-4 weeks from now. For example, if you have one plank of wood, then you have another layer of wood, then you have another layer of wood, and then you have another layer of wood, 4 layers of wood, right? And if you try to bend them, if you don't put glue between them, they will slide.
Yeah.
So there is shear stress as well. So you are right in that regard. You have
No, I was just confused about the X direction of this normal stress.
Okay, I will explain the X direction of the normal stress. So for example, if you are putting a load, pen, whose pen was that? Whose student left? I had to remember that.
When we find the maximum force, we can use the cross product.
Thank you, hocam.
Then take the theta as not.
And you will get the same thing.
No, this is related to maximum force, minimum force.
Okay.
And you already told us in the literature. So, in order to find the force, we need to multiply stress with the area, right? This represents area, by the way. Sorry.
It's fine.
So since they are into the different axes, as you show as you shown up in on slides, and take the theta as 90 degrees, and we plug it inside not 90, so which is 1, and so gx times area gives the maximum.
Okay.
Force.
If you are using the maximum,
If we plug in zero, then we find the force 0.
Oh, I got it.
When the
Area is right like this.
Yes.
Got it.
But in parallel, it's directly use 0. The force.
Oh yeah, this is what we talked about, I think,
Yes.
in the initial. Wow, it's incredible. You have
correlated both of them. You are right. This is incredible. You really have understood this well, actually. Huh? I never thought like this, by the way.
Oh,
good.
we're taking many courses, you know, so.
Probably that's fine. Nice. I'm impressed, actually. Good. Okay, I think that brings us to the end of our class. Oh. Okay, this CC prime was clear, right? We went left and right, but I was able to explain this part, right? CC prime, if you remember this question in which we were talking about K value in the beginning of the class.
From chapter 3, right?
Yeah, just today. Today we were talking about this question. So is it clear, this part? I said AB, BC, and then I said, let's name the place where the torque is acting as C prime. And you have to find CC prime actually. No? I tried to explain it again because I think we made a mistake here. You don't remember this? Let me pause this actually. So yes, I hope this is clear that in this question, it is good idea that you divide this into A, B, and C, and then C prime, then D. This means that this torque is acting at a finite distance. I don't know, 0.1 millimeter, 1 millimeter, 0.05 millimeter from this. So at the end of the day, when you have to make cuts, you have to actually look at shear stress CC prime in order for you to use the value of K. So you can put a CC prime here, and that's how we proceeded. I hope it is clear.